And what I'll be talking about, well, is interacting quantum particles in a 1D random background. So, oh yeah, the second note is that a number of you already heard part, or, well, not exactly the whole, the same talk, but part of this talk, a big part of this talk, at least one occasion. And I apologize to them, right, except to Jeff, of course, who anyway likes to have at least 2 layers of a given talk, so. No apologies needed in this case. Well, okay, so what is it about? It's going to be about, well, as the title says, quantum particles. So we're dealing with, I'll start with some general introduction. We're dealing with, well, Hamiltonians. So let's take a random Hamiltonian. So that's the random background. So minus Laplacian plus V omega on RD. Right? I won't make any specific assumptions for the moment. Come back to that later. And what we're interested is many particles, right? So how do we do this? Exactly in the same way as Günther said, or told us 1.5 hours ago. So we take, which we got is 1. Sorry, I forgot a few. H omega. Well, okay, that's what I want to write. And actually, I'll be looking at the system inside some box. So this one I call H. What do I need? 0, n. There are 4 superscript and indices. So what is H omega? So this is lambda here, lambda there. So H omega lambda is going to be H omega restricted to lambda, and lambda is something large. A large cube, for example, or if you prefer, I don't know, sphere or whatever, ball, sorry, not sphere, ball or whatever, such that we are thinking of the limit, of course, lambda is going to be sent to infinity. And so these are, so the only thing that's missing is 0 is fine, we all know what it is, and here the n is missing. So n is the number of particles, right? So it's the number of terms in this sum. So they are all the particles are in the same background, and the background is drawn from a random potential. Okay?
On the left-hand side, should it lower index omega comma lambda or omega?
All lambda, yeah. Lambda is going to be lambda equals lambda L is going to be of volume L to the D. So I think of it as a cube. You're right. I mean, you could replace L by lambda, but I'm going to write it L. Because quite quickly, D is going to be 1. Okay. So, and as Günther said, well, the whole spectral theory for H omega n is known once you know the spectral theory for H omega lambda, for the very simple reason that this thing is a sum of commuting operators, right? So, and of course, for each of the individual terms of the sum, if you know the spectral theory, meaning the spectral data, eigenfunctions, or the spectral measure, if you want, for the operator H omega lambda, you certainly know the ones for the identity, not much to be computed, right? Now, on what Hilbert space do I look at this operator? Well, we have various choices, right? We have, of course, the same as Günther, which is the Boltzmann statistics. We just look at the total product of the individual L2 lambda. We could also, so this is Boltzmann. We could look at the boson statistics, right? So here we take a tensor, a symmetric tensor product. So we just look at eigenfunctions that are totally symmetric. Those. And we could look at, let me erase this. Look at the Fermi statistics, right? So we take anti-symmetric tensor products of L2 lambda. This is the Fermi statistics. Okay, and of course the answers, as far as the spectral theory of the full in non-interacting Hamiltonian goes, depends on these statistics, right? Imposing the requirement to have only totally symmetric function or totally anti-symmetric function is going to change the eigenvalues right, and eigenvectors of your system. Okay? So I will not deal with the three cases. What I wanted to actually present today is this one, but I'm unfortunately not far enough inside this project, right, that I can actually put in. So I come back to this one, to the Fermi statistics, right? So I mainly speak about the Fermi statistics. So what do we know? So mainly, so Fermi statistics. So imagine that you know the spectral, so we are working on this Hilbert space. So imagine that you know the spectral decomposition of this guy. So let me call it E1 of lambda omega. Well, actually, I can do this. En of lambda omega. These are the eigenvalues, right? So lambda is a compact cube, so we're dealing with a second order differential operator on a compact manifold, right? We know the spectrum is discrete, it has compact resolvent, and we call Ej its eigenvalues, and phi j lambda omega are its eigenfunctions. We repeat things according to multiplicity. And then, well, we very well know that if you look at the eigenvalues and eigenfunction of H0n lambda L, well, they'll just be given as you choose. So I have n particles, so I choose jk, k going from 1 to n. Phi jk, I take the antisymmetric tensor product, right? So I choose indices jk. For this antisymmetric tensor product to be non-vanishing, right? This is supposed to be an eigenfunction, so it's not 0. Non-vanishing, we know that they are 2 by 2 distinct, right? None of the two is the same. And this is associated to the eigenvalue sum k from 1 to, sorry, this is large n of E jk lambda omega, right? This gives you the spectral decomposition of the operator H0n, eigenvalues and eigenfunctions. Okay, this forms the basis for this operator. Okay. So, what are the questions we are interested in? What are the questions we're interested in? Well, of course, the main thing I'm interested in is interactions. So therefore, what I'll do, I'll pick an interaction potential, meaning a function u from Rd to R. And I'm going to assume, which is not innocent, I'm going to assume the interaction potential to be repulsive, right? So it's going to be from Rd to R plus, okay? I won't make, for the moment, it's a bounded function, okay? To make it simple, it's not really necessary. I mean, we got Laplace operators, so we can regularize things, but let's say it's bounded. Okay, and I'm going to consider, of course, all my particles are equal, and so I'm going to consider HU n omega L to be what? To be H0 n omega L plus the sum of u xi minus xj. So each of the x's is for, xj is for the ith particle, and I less than j less than n. Okay, I'm interested in this Hamiltonian, and I'd like to be able to say something non-trivial about, okay, well, eigenvalues and eigenfunctions of H omega L U n. Right? Of course, this is fixed volume, right? So we know still we have the sum of these Laplacians, factor out the Laplacians. So we have nice Laplacians in a large dimension, right? But it's still a second order operator on a compact manifold. So we know that this has only eigenvalues and eigenfunctions, right? No other spectral type in here. And of course, well, it is a bit demanding to ask the question in this way. I mean, there are lots of them, right? So, oh yeah, there's one thing that is missing. Of course, what we want to do is, well, not consider a finite cube, but let the cube grow, right? And so what we want to do, we want to consider a thermodynamic limit. Thermodynamic limit, meaning we want to let L go to infinity, N go to infinity. They go to infinity both together. But we want the number of the particles to have a density. And rho is going to be a fixed positive number. Okay, so I want to have a huge number of particles in a large box. And I'd like to say something about what happens to the spectral theory of this operator. Sure. Say L to the D. Yeah, you're right. I'm already in dimension 1. Thanks. It's L to the D in here. Well, but of course, speaking, I won't have anything intelligent to say about actually for all eigenvalues. I'll be more modest, and I'll only consider the ground state. So I'll define E0. Well, it has again lots of indices. Or yeah, let me put the indices about at the same place. So EU of n omega L, right? Which is the infimum of the spectrum of HU n omega L, right? This is well defined. It's easy to show that, at least under such an assumption, the operator is nicely lower semi-bounded. Okay. And well, the interesting thing, as the system size increases, of course, number of particles increases, and the natural thing that will have a limit is, of course, not the energy, the total energy of your system, even in the ground state. It's going to be the energy per particle, right? So this is in the, I write it TL, right? TL rho if you want, which is thermodynamic limit with density rho. So you want to say, can you say something about this? Okay. And the other thing that we know is that to this ground state, there is, to this ground state energy, there is a ground state associated, right? So it satisfies it's normalized also. And I don't have space actually to write it. Up E U N. Right, satisfies the ground state equation, and it's normalized, and we can assume that it's not negative. Actually, here. Let me put Dirichlet boundary conditions, right? I didn't speak about the boundary conditions on my volume, but I put Dirichlet boundary conditions. Neumann is going to be fine as well, but okay. As we're going to see. And so we'd like to understand what's going on, what's happening to this in the same thermodynamic limit. Can I say something about this ground state, right? And in particular, I'm interested in two things. I'm interested in the effect of the density of particles and of the interaction on this ground state, right? When u equals 0, I know who these two are. I already wrote them on the board, right? And of course, they are roughly as complicated as the system of one particle operator is when u equals 0, right? It depends on the Hamiltonian h omega. So, but we have some information. As we see, the information that we have usually is not really what we'd like. Okay, I want to do this. So first thing, let me first do a computation, right? In the case u equals 0. Okay, let's start with, so of course, there are general things about this. First, oh yeah, there are two things I want to say. So the first thing, of course, as mathematicians, we'd like to know that these limits exist, okay? So actually, under fairly general assumptions, you can prove that this limit is going to be, will exist, right? Whether it's finite or not will depend actually on the value of rho, the value of u, but there will be a range of rhos, of densities, where this limit is going to be finite, right? And this is part, okay, so existence, so let me call this equation E and equation psi. So E, limit exists, limit E exists quite generally. And essentially there is the PhD work of Nikolai Veniaminov, and the corresponding paper in Annales Henri Poincaré. And there is some work in another setting by Blanc and Levin. They didn't consider exactly the same operator. It appeared about the same time, actually. I think it's also 13 or 14, I don't remember. Blanc and Levin, they didn't consider exactly the same framework. They looked at the operator on the Fock space, right? So they took essentially the graded Fock space above this Hilbert space, also for fermions. And what they did is, instead of fixing the density, they fixed the chemical potential, right? Which comes up to the same. Okay? And they looked at the existence of the ground state for a given chemical potential. And they showed that it exists. And the main thing is that Blanc and Levin, their aim was actually to treat the case when U is a Coulomb potential, right? So it has singularities, long-range singularities at infinity. Okay? So this exists, this limit exists quite generally. The limit psi, well, there is a problem. Because, of course, when you increase the number of particles, these functions, the psi's, increase the number of variables they depend on, right? So the thing starts being a nice function. It turns into some, well, something which is rather unwieldy, a field maybe, but it's not obvious in which sense to define a limit. So what you do is, you do it as physicists taught you, you resort to what are called k-particle. K-particle densities. Oops. K-particle densities, and what is this? Well, it's just the following. Call it gamma k of a state psi. So take any psi in L2, lambda n L2 lambda, and take gamma k of psi to be, well, you just integrate. So there is a normalization constant. C of n and k that I don't remember, I don't want to compute, of, so this is psi, it's the same psi, x1 xn minus k, or x1 xk, xk plus 1 xn, psi of, let me call it z, z, psi 1 1 yk, z1, z1 z1 to zn minus k, and you integrate respect to z1 dzn minus k, right? And I forgot the bars here. And what you get is that this thing is a nice trace class operator. So gamma psi of k belongs to S1 of, so here we are in lambda k, so this k is fixed now, L2 lambda. Moreover, it is positive, and the normalization C and K such that the trace of gamma K psi is equal to the number of K tuples of particles among n. Right? So that this is essentially representing all the groupings of K particles among n. Okay? And now, what you can hope for, so add in the additional indices here, what you can hope for is a convergence of gamma psi u n omega l k. And this is a question that makes sense, right? May not be able to answer it, but at least the question makes good sense. Sure.
So why this should be a right scale and why trace should be
But you scale it as you want. This is just because you imagine this thing is going to be, you see, it's acting on this space. It's an operator on this space. So it's really a density matrix for k particles together. So this is why you scale it in this way. Okay, so the number, this number is exactly equal. So this is C, because this has trace, if you compute it, it has trace 1. Right, if you just take this part. So this is exactly this number. The C is exactly equal to this number. But the scaling doesn't really matter. Right? It's just a natural way because you're looking at k particles, right? And so because you have in the beginning n particles, you'd like this to have exactly the right number of particles. Okay. So in this, for this question, I don't know that there is any theorem saying that this limit exists in general. And actually, as far as I know, there are only very few systems for which this, I mean for the functions, for the eigenstates, for the ground state, even for ground state, the existence of the k density matrices for the ground states as a unique limit, maybe by some compactness argument you can show that there is a subsequence that's converging, right? I mean, yeah, sure, that there are some limits in the subsequence, that's not very difficult to get out of the system, right? But that the thing exists as a limit, unique, well-defined, unique, you have unique ground state. I don't know, I'm not sure that this is...
well, uniqueness doesn't always hold. If you have some sort of symmetric representation.
Actually, for the ground state, it should hold, no? Oh, no, you're right, actually. But that the number of limit points even doesn't go to infinity is not something completely obvious. Right, even if you have some symmetry, right?
Yeah. Once it's more than one, I think it always does say because the convex combinations. At least that's how it works in classical statistical mechanics.
That's possible. Yeah. Okay.
Anyway,
that's a good point. Okay, but maybe there are some theorems that I don't know of. I just said I don't know of any theorems.
How many? How should I say independent or how many pure?
Right, the pure
yeah, exactly.
We expect to be.
Yeah.
We hope to be finite. Extreme points, yeah.
The extreme points of sure.
Extreme points, right?
Okay.
Correct.
Okay, so but there is one case one can settle with just the knowledge that we have already here. And assume now u equals 0. Okay, let's start with the non-interacting case. So, well, what's the ground state? Well, we know who the E0 n omega L is. Well, my eigenvalues being ordered increasingly, this is just a sum from k equals 1 to n. I start that one, I hope, over there. Yep, it's still on the board. Of ek omega L. Right? That's just the ground state energy for this system. It's the smallest one you can have because of these inequalities. And, of course, the ground state itself. What is it? It's the tensor product n of phi k of the same thing, k going from 1 to n. Okay, and there is normalization in there. Right, it's hidden inside this symbol. But in the random case, one can actually, this one cannot be lifted. In the random case, one can actually compute something. So I'll assume the following. Assume that my operator, which I didn't say much about, h omega has an integrated density of states. What does it mean? It means the following thing. It means that if you compute the number of eigenvalues of your operator h omega lambda less than some energy E divided by the volume lambda, well, this will have some limit n of E when lambda goes to infinity. Right? When the volume of lambda goes to infinity. So this is known for many models, consequences of ergodicity, right? Well, in this case, what you can do, so I go on over there. What you can do is you can rewrite E0 n omega L as, what is it? It's just the integral of the energy E of what? Of the counting function number of eigenvalues of h omega lambda less than e, right? It's just this. Okay? So what you can do, you want to know, divide this by n, divide this by n. Of course, this you can replace by L or by volume of lambda. Divide this by volume of lambda, right? And now you'd like to know, so this a priori is the integral, but this thing is going to be 0 above some energy E. Where do you go? Oh, sorry, I forgot to say. We go to En, from minus infinity to En. But how is En defined? En is defined as the number of eigenvalues of h omega lambda less than En. Well, this is n, right? So if you divide by lambda, n over lambda, okay? And now, if you let lambda go to infinity and n go to infinity in the thermodynamic limit, such that n divided by lambda goes to rho, well, if everything is nice, and it tends to be because this, as a function of the energy here, is an increasing function, right? So if the limit has any regularity property, you know that the limits are going to be uniform. You get from this that n of some value e rho is going to be rho, and En is going to converge to e rho to satisfy this equation, right? And this integral now will converge to what? It will converge to 1 over rho and integral from minus infinity to e rho of e dn e. So in the free case, you can actually compute this. It's just a matter of technical work to make this rigorous, but it's not so difficult using, as I said, the fact that things are increasing. And well, this energy is called the Fermi energy, right? Well, okay. Let me now say something. Come back. As well, here is the whole thing. And there's a typical property of random systems. There's a typical property of random system, which is the following, which is what? Which is that n of E behaves when E goes to, well, let's say, assume that this is the infimum of the almost sure spectrum of h omega. Right, so let's assume this is 0. Okay, let me take this to be 0, otherwise shift things in energy. Well, this typically behaves like, well, constant E minus d over 2. So it typically decays very fast. Right, that's a typical Lifshitz behavior. And if you use this in this integral, what does it mean? You integrate from minus infinity to e rho, right? Imagine that e rho, so actually, I assume that this is 0 now. Right, because I assume that the spectrum starts at 0, so dn is 0 when E is negative. And now if you're interested in E rho small, right, but remember, n is an increasing function. To say that E rho is small is the same thing as to say that rho is small. So if you're interested in rho positive but small, then E rho is going to be small, and this integral, right, is going to be essentially what's happening. So this integral from 0 to e rho of E dn of E is going to be roughly e rho so it's going to be e rho times n of e rho, meaning e rho. Right, so actually the limit of this thing in the small density regime is going to be this Fermi energy, right? This is why this thing is relevant, our problem. Okay. And so far so good. This is not too difficult to make rigorous for many systems. But what happens when you are non-zero. Okay? Well, for such a general system, I unfortunately don't have many results. Actually, I don't have any results to give you. But just some intuition, right, to start with. Oh yeah, one thing I would like to say is the follow. No, it's a bit too early. So one intuition, okay. So now imagine you want to do something very simple-minded. You want to do perturbation theory, right? Simple perturbation theory of the ground state. I mean, you imagine that the ground state of your random system is going to be of your interacting system is going to be a simple perturbation of the ground state that you know very well of the non-interacting system, okay? Well, you see that, and that's one of you see where the difficulties come from. Imagine you want to do perturbation theory. If you look at the non-interacting system for density rho, you see that even to compute just first order perturbation, you need knowledge of the ground state of the non-interacting system. But what is this? As we said, this is, from 1 to n of psi, how did I call it? Maybe phi something. Phi k omega lambda, right? And n is equal rho times L. Okay, that's my n. It's rho times L. So you need the knowledge of phi k, meaning the eigenfunctions of your non-interacting system, right? Phi k, for k going from 1 to rho times L. It means that if you look at the spectral axis, right, what are these eigenfunctions? These are the eigenfunctions going from, corresponding to the energies, going from 0 to E rho. I still assume that my bottom of the spectrum is at 0, right? So you need a macroscopic number of eigenfunctions that you can control, that you need to control at the same time. And that's one of the basic difficulties. For example, as far as I know, none of the theories of localizations that we have give you a good control for a very simple reason. For most of the theorems in localizations, prove something like this. Phi k of x is going to be, there's a constant depending on k and omega, e to the minus eta x minus x, depending on k and omega also, called the localization center. You have estimates like this. But of course, an estimate like this does not give you any information about what actually the interaction does to this tensor product, because you don't have any lower bound. You don't know if this is accurate. You don't know how big this is, how small it is, actually. So if you want to compute, for example, the interaction term, it could be, because of the localization property, that on your system of functions, the interaction term is actually much smaller than it should be. Just because these things, we know that they decay at least as fast, but they could decay much faster. Who knows? There may be some regions where they could essentially be absent, much smaller than that. And so,
in one dimension, you have no behavior.
That's actually true and false in the sense that Lyapunov behavior in one dimension is proved when what people proved in the classical Lyapunov behavior is the limit of phi k of log phi kx, right, divided by x is equal to the Lyapunov exponent when x goes to infinity in one dimension, right? But the thing is, you don't know at which x this starts to be true. Meaning that if you restrict yourself on a finite box, for which eigenfunctions inside this finite box will you already be in the Lyapunov regime? That's not known. It doesn't come from the standard theory of Lyapunov exponent, because this is all limits. It never tells you what happens in the finite box. You don't know in a finite box how close you are to Lyapunov behavior. You know that once you go to infinity, it's fine. It finally looks like Lyapunov exponent. Okay? No, but this is really true. If you check it, look at the proofs, right? And actually for some other work, I had to improve on this, right? Where you have, but that you have lower bounds, okay? Also on the eigenfunction in finite volume. But you cannot use simply the theorems as they existed, because this is just limiting theorems. It's just at infinity, right? There were no theorems on finite boxes, as far as I know, even in one dimension. Okay, so.
Why do you need lower bound? Was it
Okay, why I need lower bound? Imagine you want to compute something like this. You want to do first order perturbation theory. Right, so I want to do sum of u I less than j lambda phi k lambda phi k, right? Just to do first order perturbation theory. If you want to know what the size of this is, you better have a lower bound on the values of these functions. Otherwise, there's no way you're going to know what this number looks like, even if this one is decaying.
You can still get an upper bound on it.
Huh?
You can still bound it lower bound.
Sure, but then if the upper bound, the lower bound does not correspond, for example, lower bound 0,
Yeah.
what do you expect you get? I mean, an upper bound alone cannot help you.
But what kind of bound do you want to, do you want to get out of this option?
Well, out of this one, I don't say that any bound on this one will give you a meaningful result. But what I'm saying is that if you don't know a bound on this one, then sure you won't be able to get a meaningful result. It's the other way around.
What I'm saying is that you know nothing about it, so you
Exactly.
get nothing.
Exactly. This
Not
is
lower
what I'm
bound
saying.
to upper
No,
bound.
you know an
information.
upper bound you can find, but it's not useful because you have no idea what the truth is.
Nothing.
Even if the upper bound is fine, you have no idea. What do you want to give as a theorem? You want to give a theorem that your limiting energy is somewhere between -5 and 25? That's not exactly what you want to get, right? You'd like to get at least some asymptotic result. For example, the limit rho goes to 0, the energy per particle looks like this. Okay, otherwise there's no way you're going to be able to measure what's the importance of the density, what's the importance of the decay of the interaction, right? So even to do the simplest minded perturbation theory, these estimates that we got for localization are absolutely useless, right? In this respect, if you want to crunch any numbers out of it, it's just a fact. So yeah. Now, as I said, one of the difficulties is that if you really want to do this as precise as possible, you need to control too many eigenfunctions. But is this actually true? Well, not exactly, because there are a huge number of particles inside your system. So what you could do is, instead of trying to control all the eigenfunctions in which the particles may be living, you could try to control a vast number of them. Right? So there's a small fraction that you need to know how much it is that you leave out, but many of them you need to control. So what I'm going to present you now is a system where you can do this, okay, which is actually a system that many of you have met before. After this somewhat lengthy introduction. So okay, let's do t equal 1, and let v omega of x be of x minus y d mu y, where this is a Poisson potential. Well, let's have intensity 1 to fix things, right? So it's just random points thrown independently on the real line in such a way that the average number of points per interval of length L is going to be L. Okay? And setup, the remaining thing is the same thing. Look at the same operators, right? Just with this potential. Okay. Well, it's well known. What is known? What is known is, first, it's known that if you look at minus Laplacian plus v omega, well, IDS exists, right? You even have, I think it's Molchanov or Pasteur, I don't remember which of the two, is that this is e to the minus some constant, e to the minus d over 1 over 2, 1/2.
You're already in d equal to 1.
Yeah, I'm d equal 1. This is d equal 1 is here. IDS exists, this is true any dimension, right? But this asymptotic is going to be true only in one dimension. There is such an asymptotic in higher dimensions as well, not due to the same people. I don't remember whether it's Molchanov or Pasteur and collaborators. I think it's Molchanov. Okay, first the IDS exists. The second thing is, it's no, yeah, I'm not sure. Not for this one. Yeah, but not for this one actually. But not for this model. The second thing is that we know that there is localization. And the sun localization first, this is work by Günther Stolz. And there is also dynamical localization, which is much more recent, which is work by Germinet, Hislop, and Klein. Right? You did it in higher dimensions also, right? But it's not. But unfortunately, it doesn't provide you with estimates better than that one. Actually, the estimates are even worse than that one, but that doesn't matter. It doesn't really matter in this case. Okay. So now the first two things I want to do is I want to present two results on this operator. This is one-dimensional theorem. Well, n of e can be written as e to the minus c plus c. Actually, I think it's a minus here. C0 is going to be positive. Let me remember. No, it's a positive. It's a plus. Plus C0 plus sum of ak e to the k over 2. K larger than 1. And C0 is a positive number. So you have actually, for this thing, you have a complete asymptotic expansion at 0 for the density of states. Right? So you have a much more precise idea of what the density of states is doing.
You wrote equals. Do you mean, and then but you said asymptotic expansion?
Sorry?
You wrote equality, but you said asymptotic.
No, but it's an asymptotic expansion in the sense that this is an asymptotic expansion. That is not a converging analytic function. This so it means that if you take this one, you subtract this with finite k terms, right? You get something which is growing to 0 faster than.
Can you erase the equal sign and put a tilde?
No, this is correct. And this just means that n of e times e to the minus c e to the minus 1/2 plus c0 inverse minus the sum k going from 1 to n.
Equality.
Huh?
Just have to define what
Exactly.
an equality.
This thing is little o of e to the k over n over 2 plus 1/2. This is what it means. That's the standard meaning of what an asymptotic expansion is.
Yes.
Okay, so this is equality. Yeah.
Go ahead.
Okay, this is standard meaning, but this is what this equal sign means if you want.
Depends on your definition of is.
Huh?
It depends on what the meaning of is, right?
Yeah, sure. Okay. That's fine. You don't like me to use the sign. Okay, so you want me to use a different sign? This one better? Oh, if you want.
No.
But I defined it, yeah. So, of course, the expansion is not converging. Okay. The second thing that you get is you get local statistics at the band edges, meaning that if you look at the process, you take the eigenvalues, so defined as before. So we're in one dimension, so they're all distinct. And you look at, so I rescale them in a somewhat different way, you see why? Sum of L times, so I take the density of states, I apply it to the jth eigenvalue, I put the Dirac mass here. L omega, right? And I take the sum over all j's. Then this process goes to a Poisson process of intensity 1 on the real line, okay? And you see the difference with the usual asymptotics, right, is that at this point, this is at 0, at energy 0, at the bottom of the spectrum, n prime of 0 equals actually n k times differentiable at 0 equals 0. N has all its derivatives. The density of states is vanishing, and all its derivatives is vanishing. This comes from this exponentially fast, right? Density of states here is exponentially decaying. So all the derivatives is vanishing. So this is why here I do not divide by the density of states as 0. Right? I really look at this one, you have to transform it through density of states. It's not the linear behavior here. It's really the density of states. So what does this mean? What does this mean? So this is moral only, right? I didn't prove that density of states were differentiable. So what does this mean? This is the same thing to say that if I look at E1 at L omega, this converges to some value which is a constant divided by log L squared. You can compute the constant from the formula up there. Almost surely when L goes to infinity, right? And it gives you information about what's happening to EL omega minus this constant, log L square. This is going to converge to some random variable that you can estimate is going to be converging to 1 over, this is going to be 1 over log L to the cube times some random variable, psi1. And the same thing for all successive differences. Right? So what you have is, because another way to say it is that because the density of states is not linear at the origin, what you will have is that this process converges to a Poisson process, but not of fixed intensity. The intensity is going to be a function on the real line, right? Non-trivial. So it would be not a function, a measure. It has density. Okay, now, so that's for the non-interacting system. Well, what I wanted to say is, okay, maybe I'm gonna, as we already have the interacting system, maybe I should give you theorem. Again, I already have all the objects. Now let's assume you, okay, interacting system. So remember, the general thing I defined before tells you that if I look at the non-interacting system, this converges to E0 of rho that I know how to define. It's just where N of E is the density of states I had before, right? Then the theorem is the following. Theorem, if I look now at 1 over N, so first thing, assume, to make things simple, U from R to R plus, U not identically 0, and let's assume U bounded. You don't really need it to be bounded, actually. You can have decay at infinity. You don't need we use it bounded, but you don't really need to. And the other thing is that I'm going to make things simple is to assume that support of U is compact. Right? Take non-trivial interaction, but it has compact support. Then 1 over N EU N omega L. Well, this has a limit. I already said so. E0, sorry, this is EU of rho. And this has an asymptotic expansion when rho is small. And the first term is, of course, what you'd expect. And the second term is what I don't remember. Gamma log rho squared times rho 1 plus little o of 1. Right, so this is an asymptotic. This is the value of this limit when rho is small. Okay? And what should I do? Should I say, actually, yeah, okay. You can, yeah, actually, under this assumption, you can say a little bit better. You can say that this is a large O of 1 over log rho, right? You can say a little bit better than O of 1. Okay. And now, if I want to describe, so here I met the first goal, right? I tell you what the ground state energy is. So I tell you how it depends on rho to first order. I didn't tell you how it depends on U, because U is hidden inside the constant gamma. So how does it depend on U? Let me explain you what gamma is. Yes?
What is raised to rho here?
What is?
What is raised to the power rho?
Log rho. Log 2. This is log rho to the power 2. This is times rho. It's a factor. It's gamma times rho divided by log rho squared.
And to the right?
small.
Oh, this is for rho small.
This is only hold for rho small. This is going to be small for rho small.
That's what the further
This is for
Sorry. Just says that this asymptotic expansion is for small rho, right? So let me tell you what gamma is. Okay. Well, gamma is the following thing. So the thing is, I have to make a choice. Actually, no, I'm not. I won't tell you what gamma, but gamma depends on you. Gamma depends only on you. Gamma is a function of u. I won't tell you what it is because I'm going to take too much time. I want to finish on time. I'd like to describe what's happening to the eigenfunctions, to the ground state itself. So imagine your random system, a random potential. So you have these Poisson bumps, right? I put Poisson points somewhere, I have Poisson bumps. So remember the talk by Nadia Sidorova yesterday? Well, it's essentially the same if you replace horizontal by vertical. Meaning that here, when I have a big chunk of space where there is no bump inside, it corresponds to the high values of the points she had yesterday in our talk. Meaning where her random process is going to live. Okay? So you have these bumps. Now you want to put an eigenfunction in there, and you want it to have low energy. Why low energy? Because the energy should be below the Fermi energy, right? It should be as low as possible. Okay, so look at this. The only way you can put something is inside such gaps, right? When you have clearings, inside such clearings. Well, which clearings? So let me call, so these are the distances LK, LK plus 1, and so on. Sorry, this is LK. LK plus 1, so it's the distance between two nearest. Plus 2, and so on. Okay? So the first thing I want to describe is roughly what do the first rho times L eigenfunctions of the non-interacting one-particle system look like? Right? What do they look like? Well, they look like the following. If instead of these bumps you would have Dirichlet walls, very simple, you would have a sine function, you just take the largest possible length, right? You take rho times L of them, and you'd have for each of them a sine function. Here the picture is going to be different because these are not hard walls, these are soft walls. So your eigenfunctions may penetrate. But roughly what you can show is that if you take, there are all mathematical results behind that, right? So what you should look at is L rho. What is L rho? L rho is the smallest length such that if you take a Dirichlet, if you take minus Laplacian on 0 L rho, you have an eigenvalue less than E rho. Okay? So that's smallest length. And of course, because this is for hard walls, here it will not work if you just have L rho. You need to enlarge it a little bit. Okay? But let's take all the LKs that are larger than L rho. Okay? So I have one here, for example. I have one here. There may be one next to it. Okay, I have another one. But typically, if I have an LK which is of size larger than L rho, imagine L rho, so of course L rho is going to be of size log rho, because this is 1 over log rho squared. It's written over there. So it's going to be big. Okay? So because of the Dirichlet points, Poisson points, if you have one of these LKs which is larger than L rho, typically there will be a large patch of space around it where no other is going to be of size large L rho again. And typically the distance that will separate you from the next large interval will be of size minus L rho. This comes from just the fact that you're dealing with exponential random variables, right? These lengths are roughly exponential random variables. So you have a large size. So what you're going to do, and of course it's not always true. It can happen that very close, and it will happen, and there'll be a number of instances, that you have two LKs, right? Even LK prime, where you have that are next to each other. there is only one bump, actually there's one bump separating them here, where both are larger than L rho. This can happen, and it will happen, because the length here doesn't depend on rho, and it's going to infinity. So how often is this going to happen? Well, this is going to happen e to the minus 2 L rho, roughly, times, right? Because the length probability is exponential, times L. So this is like rho times n. So it doesn't happen very often. This is roughly, if you look at this, you get that this is rho squared times L, and rho L is n. So it's only very few of those, right? You need n of these things to get your ground state. You need the n lowest. But for a few of them, of course, they are going to be close to one another. But it's not many, okay? And so what you can show is that if you're in this situation or in that one, what you can do is you can cut off your Hamiltonian, but not at L rho. Not by putting Dirichlet boundary conditions here, but by putting Dirichlet boundary conditions inside the sea here of perturbations, where you actually have a Lyapunov exponent which is going to be pretty large, and that is going to decay over all this distance. What does it mean? It means that this system of particles is going to be effectively replaced by minus Laplacian with Dirichlet boundary conditions on 0 L prime k, where L prime k is going to be roughly Lk minus some constant. The constant comes from the width of the potential here. Okay? And here, what you can show effectively is that you have a very precise picture. You have a very precise picture of what the eigenfunction in here is. Here it's going to be a nice sine function, and here it will have exponential decay, and you control everything. Okay? And in particular, when two things here are very close, you are able to control how these things overlap and how they interact. And you're not only able to do this for the ground state, but also for higher excited states. And the larger the interval, because Lk larger than L rho, it could be 2 L rho, and actually it will go from L rho to what is the largest interval that you get is roughly log L. Right? Up to this, you can control everything essentially uniformly. Right? The price you pay for that is that you don't care about what's happening in there. I don't care whether the things are localized or not. I'm going to replace the true states by these approximate states. So I'm not interested in localization at the large distance. I'm just interested in what's happening where I can get a precise picture. I'm sure you can actually couple this with localization and get that the exponential decay goes on, but that we don't need to do it. And what you show is that if I look at the eigenfunction, the one particle density matrix for psi 0, the non-interacting ground state, and you take, so this is the projector, this is the orthogonal projector on all eigenstates up to level n, and you replace this by these approximate eigenfunctions, right? You take the projector on the approximate eigenfunctions, of which I explained briefly the transformation. Then you look at the difference of these two trace class operators in trace class norm. This is going to be small in the sense that it's going to be smaller than rho times 1 plus theta times the number of particles. So there are very few particles that don't look like these. There are, but very few of the particles don't look like these. Right? And what does this one look like? Well, an easy way to represent it is the following. This will be the last thing I do. For psi 0, you can look at, here's the length of the intervals. Here's the length of the intervals, right? And what you can, or actually, here is not the length, but it's the modified length. It's this L tilde, right? You look at the L tilde k, and you distribute the L tilde k's for each pieces. So these are what I call the clearings, each of the clearings. You look at where L tilde k falls on this grid. And what you show is that if L tilde k falls below L rho, in the ground state, it will not contain any particle. If L tilde k falls below, inside L rho and 2 L rho, it's going to contain one particle. If it falls inside 2 L rho and 3 L rho, it's going to contain 3 particles. And so on. Okay? Let me now show you what happens to the interacting ground state. The interacting ground state, what it does is the following thing. So I draw it in green. I hope everybody, well, actually in yellow. It's going to be easier to see. Well, the interaction ground state does the following. If you have 2 particles living together, they feel the interaction quite strongly. It's repulsive. So what's going to be the case is that the particles that were living together here will be taken out, right? And they'll be replaced in some pieces that were too small to contain any particles for the non-interacting system, meaning here. Right? So this contains, so that's the interacting. 1, 2 for the interacting. And here you kept 2. But here, inside the interacting, the 2 particles, these were 2, there are no interactions. So these were 2 free particles. Here, these are truly interacting particles in the sense that they are, if you want, in these intervals, these are the L tilde case corresponding, they are solutions to minus d2 dx to d2 dy2 plus the v omega x plus v omega y plus u of x minus y. You have your interaction, and you look at the true ground state of this one. And the ground state of this one does not factorize. Right? This is entangled at this level. Okay? And so that's the statement of the theorem in the picture. And of course, well, I don't know, I did not do the analysis, but what you can do is that if you fix any k here, you can go up to any level k. So in the blue one, it goes on. And if rho is small enough, the picture here is going to be correct. So it's going to extend here and start here and go on. Okay, and this is, if I fix k for rho small enough, this picture is going to be correct. What I don't know how to do yet, what, for example, would be necessary if you want to compute the entanglement entropy for the ground state, is to get this picture for all k for a given rho. For the moment, I fix k, I know how to find rho small enough so that this picture is correct. If I knew how to do it for any k for rho small enough, I'd be able to compute the entanglement entropy, right? Because I would have a very good description of exactly how the particles are displaced in my ground state. Okay, thanks very much for your attention, and sorry for passing my time.
We will have questions, but while you still have your attention, before the question, let's thank the organizers, both the major and the minor. Now we can ask questions.
What is the actual statement for the interacting system? When you say
the actual statement for the interacting
these
system is that if you look at the one particle density matrix, right, then what you can do is you take the states computed in this way. So here you have one interval, right? You just take a one particle matrix. Okay, you compute the ground state. Here you take the 2 particles that I wrote here. You compute the ground state. And now you construct the anti-symmetric tensor product of all of these, right? And then if you look at the true ground state one density matrix, remove this anti-symmetric density product, the one particle density matrix for this anti-symmetric product, you get something which is small.
small in the same way that was?
Small in the same way as this one, exactly, in the sense that it is smaller order than the number of particles that you move. If it wouldn't be smaller order than the difference, you wouldn't have done anything. Right? But it is smaller order than the number of particles that have been displaced.
Okay.
And you can actually here, if you do the same on, what changes is the power here. Instead of getting 1, you get 2, 3, and so on. Right? Every time you go one of these ladders up, you get a higher power in K. And of course, if you could let this power go to infinity, well then, this could be made much smaller than actually the total number of particles, which is the ultimate goal. And you'll be able to control really the system at the level of precision where you can compute the entanglement entropy, for what is already a rather complicated system.
Sure. Is it just standard that all the k-particle density matrices exist, the limit exists?
Well, yeah, from this, it's in this system, yeah, you can show it actually. You can show that that they exist. I don't know of general result, but in this case, you can show that it exists. You can actually compute them. It's easy. At this level, you see, if you go to this level of precision, what happens for higher K-density matrices is actually disappearing. You don't see it because you only control two particles together. The remaining things are all in the remainder terms. So if you go high, you need to, if you want to really control K-particle density matrices in a meaningful way, you need to go higher up in this ladder. Otherwise, you just don't see anything, right? Because they are trivial. I mean, if I look at, for example, in this picture, if I look at a 3-particle density matrix, it's going to be only computed from these two things, which contain 2 and 1 particle. But you already know everything about those.
No more questions. Let's thank the organizers again.
Thanks very much.
I have a quick